So this is from the CRC. Let's go to the end slide of last time's notes. We're talking about TX phase diagrams. And this is in a section of the CRC talking about azeotropes. So they wanted to clarify the terminology of low boiling heterogeneous, low boiling homogeneous, and so on. So these are many of the different types of liquid equilibria that you could have. And let's just go through a few of these. This one here, the low boiling, this one and the high boiling were the two that we covered in the notes. So we looked at a low boiling azeotrope where the azeotrope had the lowest boiling point. It was lower than pure A or pure B's boiling point. And you can see that. Here's the boiling point. If this is the mole fraction of A across the x-axis, this would be A, and this would be B, and this would be the azeotrope's boiling point here. And so that would be the low boiler, the high boiler, the azeotrope would boil high. Now, they went ahead and produced the PX diagrams, and you can see the PX diagrams because we're dealing with pressures now. You know, the low temperature gives a high pressure because it's more volatile. So the partial pressure is high if it's boiling low. Remember, it boils whenever the pressure reaches 1 atmosphere. So if it's got a really high pressure, it's going to boil at low. It's going to reach 1 atmosphere at a lower temperature. Okay, everybody cool with that? Now, this diagram far to the left is a really useful one. It's YA versus XA. And so it's the mole fraction concentration in the gas plotted versus the mole fraction composition in the liquid. And so let's, here, if you look at it, starting over on the left, so here is YA and XA equals 0. Now this line that's just a straight line across, that's a perfect situation of, we'd say, Raoult's law, where the gas composition and the liquid composition are the same throughout. But in reality, you have, in this region, the gas composition is enriched in A, and then it's depleted in A. And where they equal each other, that's the azeotrope, because that's the definition of an azeotrope. When YA and XA are equal, then they are azeotropic. Okay. And so then we have these other things. Let's look at some of these other situations. Here's a low boiling heterogeneous mixture. So we're going to talk about these today. It looks like an azeotrope. See up here the vapor line is dashed. So it's a low boiler, and you have the vapor lines here. But down here we have these two dots. And so between those two dots is a two-phase region. So we'll talk about phase separation in the liquid state today. And then we'll talk about the vapor above that phase-separated liquid. And then when you enter that into the mix, then you have partially miscible, low boiling, high boiling, partially miscible. So when you see these little dot regions here, those are two-phase liquids. So these three are heterogeneous. And then there's some crazy, I mean, it's a possibility. I don't know of any mixtures, but there's a possibility that you could have a double azeotrope. And so it's easy to see the double azeotrope over here. YA equals XA in two spots. And one of those is a high boiler and one of those is a low boiler. So let's dive into partial miscibility. So that'll be today's set of notes.
What do you mean when you say a two-phase liquid?
Just like oil and water.
Oh, okay.
Two liquid phases.
Gotcha.
Yeah, so when we say partial miscibility, there may be a temperature region where it's homogeneous. At all concentrations, there's no phase separation, so you can go from mole fraction of oil and water from 0 all the way up to 100% oil, and you wouldn't have any phase separation. So that would be a homogeneous mixture, and it would be miscible. So it's one phase at all concentrations. But if you cool that down, you get two layers.
Yeah.
Yeah, and so then you have phase separation, and that would be partially miscible. There's a region where it's miscible, a temperature region where it's miscible, and a temperature region where it's immiscible or heterogeneous. So miscible means it's one phase through all compositions. So water and acetone are miscible. You can put in, like you can have 1% acetone, 50% acetone in water, or 95% acetone in water, and it's one phase the whole way. You don't get phase separation. Okay. But if you cool that down, there may be a temperature region where you do get phase separation. Okay. Same with ethanol and water, and methanol and water. Those small alcohols in water are miscible. But you get up, you keep lengthening that organic chain, and eventually you start getting phase separation. And so classically you have the water octanol partition coefficient. That's definitely a two-phase situation where fat-loving things or hydrophobic things will go into the octanol layer, and hydrophilic things will go into the water layer. And we use that as a mimic physiologically for fat-soluble drugs or water-soluble drugs. And we'll talk about the water octanol partition coefficient. So water and octanol is a very well characterized, partially miscible system. Now we use this in miscibility because a lot of times when we want to distill things that have a really low vapor pressure, in order to heat them up, like an oil, to heat that up until its vapor pressure is 1 atmosphere, the oil will decompose before it reaches a boiling point. And so how do you separate things? And this is really popular now, the essential oils, right? Mm-hmm. Where do we get the essential oils? Peppermint oil and all that stuff. They're extracted from plants, different kinds of flowers and leaves and so on. But those oils cannot be distilled away from the plant matter by themselves. Because if you were to heat those oils up to try to get their vapor pressure up to 1 atmosphere, you're going to have a problem. They're going to decompose. So there's two things you can do. You can reduce the ambient pressure. So it will boil at, say, 1 torr if you have a background. If you have a distillation apparatus that has a pressure of 1 torr, and you can heat that system up to where the oil has a vapor pressure of 1 torr, then it'll boil at that really low temperature, and you can get it to come over. So that's a vacuum distillation. So you can reduce the ambient pressure with a vacuum, and you can put a cold trap over here so it doesn't go into your vacuum pump. And when it hits that cold trap, it freezes out. And so it would be vacuum distillation. That's a great way to distill things that are not very volatile. And the other way is steam distillation. So you mix these two things together, and if the mixture has a pressure of 1 atmosphere, then it will travel and it will distill. And so you can spray steam into this leafy mixture, and the oil and the steam together will have some vapor composition that has some of that oil in it, and that oil can come over with the steam. And the steam temperature is not enough to decompose the oil. So steam distillation is probably the most popular way to extract these oils. And it's very common. I found this out in Oregon when I was a graduate student. They had peppermint fields, just huge fields of peppermint. You see that it's like a weed around here. You can find it. And we have some in the backyard. You peel the leaf off, put it in your tea. It's nice flavor. I wash it a little bit. You never know if a cat's been around. So the peppermint oil comes out of the leaf, gets in your drink, tastes really nice. Well, they had this huge fields of peppermint, and they would come and harvest the peppermint oil, and you could smell it. It was wonderful. Yeah. And then they would go steam distill it, and then all this mushy steam distilled leaf plant matter had really broken down from the heat of the steam distillation. The peppermint oil was removed, and they come back out with dump trucks of that stuff and just dump it back in the field for fertilizer, but also for compost. So you could go get steam distilled peppermint leaf matter to put into your compost pile. Best smelling fertilizer you've ever had. Way better than manure, in terms of the smell. Now, I don't know about its nutrient content, but putting steam distilled peppermint leaves in your compost pile is definitely a plus. So I just had a little slide on steam distillation just to talk about other methods of distillation and using partially miscible or non-miscible situations. If you can get it up to ambient pressure, then it will distill. You can lower ambient pressure, or you can use steam to raise the vapor pressure of this mixture. Let's talk about the Gibbs energy of mixing. This is the equation we talked about last time. Well, actually, these top 4. But for the homework, for an ideal solution, this would be the one that you're going to use for your homework, calculating the the Gibbs energy of mixing for 2 and 3 components. And so you're just adding up those natural log pieces for the different components. I think I have you do a 70-30 mole fraction, so 0.7 for one and 0.3 for the other. And then I have you compare that to a 0.5 and a 0.5. And so you calculate which one of those is more negative, which would mean more spontaneous. And so is it more spontaneous for a 50-50 mixture to mix together or for a 70-30 mixture to mix together? And then I have you do a 3-component where it's like 60, 20, and 20, and 33, 33, 33. So to see which one of those is most negative, and then just have you think about it and write your own, reactions to what you've done mathematically. Now that's the Gibbs energy of mixing if delta H is 0, so for an ideal solution. But the one model for calculating the enthalpy of mixing is using the Hansen Solubility Parameters. And so you can put in these total solubility parameters and the molar volume of the system components, and you can calculate this delta H value. And if you'll notice over here, we have three lines plotted, and this is mole fraction of nitrobenzene in hexane. So over here at 1, we have pure nitrobenzene. Over here at 0, we have pure hexane. We have delta H plotted here, okay? And you can't really tell it, but that delta H is not symmetric, about 0.5. It's to the right a little bit. So the maximum is over here. It's not right at 0.5. And that's because of this difference in the molar volumes of the two substances. So hexane and nitrobenzene have slightly different molar volumes. And so that's a difference in the way those two molecules like each other, right? And because of this difference in intermolecular attractions, you could have phase separation. If those molecules liked each other the same as, like nitrobenzene had really no preference for other nitrobenzene versus its preference to hexane, then you would just, if that was the situation, that'd be an ideal solution. But since there's a slight difference in the way nitrobenzene bonds to itself and hexane bonds to itself, you can get phase separation at a certain temperature. So the Gibbs energy of mixing is this blue one here, and that is just a very symmetric curve. And I'm kind of giving you the answer to the homework. Here's a 50-50 mixture, and that's the most spontaneous mixture. That's the low point on this delta G line. Oh, that's the lowest on the T delta S, the delta S line. If enthalpy was 0, that'd also be the minimum delta G. But in this case, delta H is not 0. And so the T delta S is symmetric, the delta H is not symmetric, and the Gibbs energy is the difference between those two. So this green line is the delta G. So there's places where delta G is negative, and so that would be a homogeneous mixture in this region. There's places where delta G is negative over here, but in this middle part, delta G is positive. So when you have delta G positive of mixing, you don't have mixing. But this is the delta G of mixing. So if delta G of mixing is positive, they separate. Yeah, when you have negative delta G of mixing, they mix. When you have a positive delta G of mixing, they don't mix. So you have phase separation. When you have delta G of 0, that's equilibrium. So you have equal rates of hexane going into nitrobenzene and nitrobenzene going into hexane. And so right here you have an equilibrium point. Right here at just less than 0.4. And right here at around 0.8 you have an equilibrium point. And so that's the equilibrium of the nitrobenzene-rich phase, and this is the equilibrium of the hexane-rich phase. So you have two layers. One has mostly hexane, one has mostly nitrobenzene. Notice they're not pure nitrobenzene and pure hexane, because these circles are not all the way over here at 1 and 0. So this, even though we say this is the hexane-rich phase, it's almost 40% nitrobenzene. You see that? And then over here, this phase we call the nitrobenzene-rich phase, it's 20% hexane. Now, this was all done for a particular temperature. And so if we use this green curve and we change the temperature, we'll see that those points either get further apart or closer together. Eventually they join and they're the same point. And then above that, delta G is negative everywhere. So this plot down here is these little 0 points plotted with respect to temperature. So here's now temperature on the y-axis, and these are those equilibrium points for the different phases. And so this particular temperature is shown right here, 300 Kelvin. So we have the 0.8 and the 0.38 points shown with this delta G curve. If we raise the temperature, then delta G drops a little bit because the entropy drops. Remember, T is the entropic term. If we raise that temperature, it's negative. It pushes delta G more negative. And so we can overcome these intermolecular attraction differences just by raising the temperature and pushing that entropy term lower and making delta G negative. So eventually then we get a region where it's miscible. Above 320 Kelvin, this region is homogeneous all the way across. You can mix nitrobenzene and hexane at any proportion and have a single phase. Everybody okay with what's going on? Now, this right here at the bottom is our temperature composition phase diagram. So Tx, mole fraction of nitrobenzene and hexane. So Tx phase diagram, and it's got this line on it, this phase separation line. So this is our phase diagram for partially miscible liquids. I just wanted to show you the delta G parts because that's where that line comes from. It's where delta G slips from negative to positive. So in here, we would have a delta G less than 0, delta G greater than 0. This is mixing. And this is delta G less than 0. And so when that delta G of mixing is greater than 0, you have phase separation. It's temperature dependent, so you could raise the temperature and have this thing called the upper critical solution temperature, or also called the upper consolate temperature. Consulate sounds like a foreign affairs office or something, but it's not. So it's just the composition. Upper consolate temperature means that it's going to be homogeneous above that temperature. They got away from the critical solution temperature because it sounds like a critical point. And it's not a critical point. It's not related to critical point at all. Okay, but I will still slip and say the upper critical solution temperature because that's the way I learned it. Okay. And so when we're talking about that, it's just talking about where it becomes homogeneous. Above that upper critical solution temperature, you have a homogeneous solution. Okay, and below it, you could have phase separation. You do have phase separation. Okay. So in this region here, we have 2 phases, and these are their compositions. So if I pick this temperature right here, then I have phase A prime and A double prime. So I have two layers in the liquid. I have this composition here, and I have that composition there. And if I have this phase diagram, then I can look at those mole fractions and tell you what the composition of each phase is. Now, up to this point, you probably, I don't know, did you have the assumption that these phases, if you had a phase separation, that it was pure substance 1 and pure substance 2, like water octanol, the 2 layers, pure water and pure octanol? I mean, they might be a little dirty, but it can be dramatic. It can be 40% of the other phase in one phase. Yeah, so that's quite a ways from. So in this case, it was 40% nitrobenzene in the hexane layer. So it's not pure hexane. It's 40% nitrobenzene. That's pretty dirty when we talk about dirty solvent. It's 40% dirty. So, you need to look at the phase diagrams if you can find them and know what your layer compositions are. Let's say you don't have a phase diagram. Well, you can just take a sample of that layer, run it through a liquid chromatograph, and get the ratios of the peaks. And so then you would be able to calculate the composition of those. And if you change the temperature and sampled those with LC, then you could map out the phase diagram. So if you had a system and you were dealing with, instead of a water octanol partition coefficient, let's say you were doing water or ethyl acetate, you may want to characterize that phase diagram. And you could do that by changing the temperature, making sure it's a stable temperature and it has time to come to thermal equilibrium. And then you could sample the compositions of the two layers and then inject those and analyze them. So let's talk about these different layers. So above 292, let's talk one more term here, this thing called an isopleth. We have a new iso. We had isocore, isobar, isotherm. Were there any others? Yeah, isocore, isotherm. Okay, and now we have an isopleth. Where does pleth come from? Pleth. You've used this word, you try to sound sophisticated. You've used this word. I have a plethora of books in my library. Right? It's amount. I have a large, so it's an iso amount, an isopleth. Okay, and so following this line up here, let me find my little marker. This dotted line right here is an isopleth. And so how does that come into play? Well, this is when we get to use that term ZA. So ZA, or actually we've got X. We're using B on this one as the far right, so let's do ZB. See, the right-hand side is B, this is XB. Yeah, so let's use ZB. And so let's take this solution right here and cool it down. It's cooling. All of a sudden we have phase separation. We get to right here. In the whole flask, we still have ZB, but it's split into two layers. And so we have layer A and A prime and A double prime. But the whole flask hasn't changed its composition. The layers have different compositions, but the flask is still ZB overall. Okay, and so that would be the overall composition. Following that line vertically, so a vertical line and a TX and a PX phase diagram is called an isopleth. Okay. Straight across would be an isotherm. Up and down, and this would be called an isopleth. So in this case, we have Zn, so nitrobenzene, so Zn is 41.41. And so above 292, that's when it hits this phase separation point. So up above here, above 292, this is what our solution would look like. And which 0.41 mole percent nitrobenzene and 59 mole percent hexane. And it's 100% homogeneous. So we just have one phase. We cool that down to 290. Okay. And the thing splits apart and we have two layers. So coming over here, that spot where it just follows this line down, if we keep cooling it, that line's going to get more and more rich in hexane. You see that? And if we cool it down, this line's going to get more and more rich in nitrobenzene. So that kind of makes sense. As we cool things down, the layers get more and more separate in their composition. If we warm it up, they get closer and closer together until it's homogeneous. Okay. And so this is just analyzing this two-phase liquid situation. So layer A. Now, which layer's on top and which layer's on bottom? Okay, this is the density of the two layers. So the more dense layers on bottom, you can't always say oil's on top of water, because if that oil is more dense, then it's going to be below water. If you have chloroform, chloroform is going to be below water. If you have ether, ether is going to be above water. So you can't always just say the aqueous layer is on bottom. Okay, so you need to know something about these two layers and their density. Here we have hexane and benzene, but with a nitro group on it. And the nitro groups do add a fair amount of mass to the molecule. So the nitrobenzene is more dense than the hexane. So the nitrobenzene-rich layer is going to be on the bottom. Okay. And so this one is going to be the lower layer, A double prime, and this one's going to be the upper layer. Now again, it depends upon density. You can't always say the right one is on bottom and the left is on top. You got to know which of those layers is more dense. If you don't know and you're doing a problem and you're worried you got them backwards, then just, make a guess, okay, and tell me which one you think is on bottom and go with it, okay. So this top layer, A prime, is hexane rich. It has this XN of 35, so that's the composition of the nitrobenzene. 1 minus that is the hexane composition. And then layer A double primes on bottom, it's over here at 0.83, that's the nitrobenzene composition, so 1 minus that is the hexane composition. Now what I want to know, and what we need to use the lever rule for, is how much of each layer do we have. Notice how I've drawn it. I've drawn a lot more A prime than A double prime. Do you see that?
Mm-hmm.
Why did I draw it that way? I wasn't just goofing around.
You're at 290, right? So
Yes.
you have to follow the temperature on the graph, and you can see that it's more rich in hexane than it is in nitrobenzene, because there's only about like 30% of nitrobenzene in the overall, right?
Yeah, for layer A prime, 30% nitrobenzene, but that's just the composition of nitrobenzene in that layer. I'm comparing how much of each layer I have. So look at how much A prime there is. That whole layer is huge, and the nitrobenzene rich, the A double prime, is very small. How do I get those relative amounts? So I can do this. I can do these 4 compositions without knowing how much of each layer I have.
Yeah.
Okay. Because I get these numbers just from these 3 numbers here. I have 0.41 overall, 0.35, and 0.83. So I can get all of the compositions of the layers, but I can't get how much of each I have. How many total moles are in the top layer? How many total moles are in the bottom layer? Do you follow the question? Yeah. And that depends upon where my isopleth is. The composition of those layers won't change, but the relative amounts will. Let's say I had, instead of 0.41, I had 0.61. So I was over here. The composition of this layer didn't change, and the composition of that layer didn't change, but the relative amounts would. Do you see and this is why I'm spending a lot of time on this today, because it can be really confusing. We have lots of different amounts. We have, in each layer, 2 different amounts of nitrobenzene and hexane in each layer. But we also have how much of each layer there is. Where do I draw this line? That's really the question. Where do I draw this meniscus? Because if it was up here, I could still have the same compositions. I would just have different relative amounts of each layer. You can figure out where to draw that line using the lever rule. So the lever rule is treating this isopleth as a fulcrum, and treating this region, this 2-phased region, as a seesaw. So I've mentioned that before. Kids these days don't play on seesaws, I don't think. So there's a chance you don't know what I'm talking about.
Seesaw. Yes.
So in order to get the seesaw to balance, you need a big kid on this end. Do you see that? Now look at the phase diagram. In order to get that lever to balance, A prime needs to be big. So A prime is the big layer. Because A prime is over on the left side of the seesaw, where there's just a tiny little piece of wood. And to balance this out, this is a small distance, and so you need a big kid. And this is a big distance, and you need a small kid. Okay? And so that's how you know which layer is more abundant, by knowing where the isopleth is. We're at 0.41. If we were at 0.61, we'd be more over here in the middle, and the kids would be about the same mass. Okay, now instead of mass, we're using total moles. So total moles of A prime times the length of A prime is equal to the total moles of A double prime times the length of A double prime. So that's the lever rule, and this is the middle point where you calculate those lengths. And so we can take 0.41 and subtract 0.35 to get that length, and we can take 0.83 and subtract 0.41 and get that length. And that ratio will give us the ratio of total moles. And so I have the math revealed here as we go through the notes. I know that I'm answering questions you didn't come at this with, and so it's kind of difficult from a teaching standpoint. I have to introduce the problem to you and then solve it. But if you didn't come to it with your own curiosity, it's not going to stick. And so have I captured the question for you in your mind? Where do you draw this meniscus? Where is that meniscus is what we're trying to answer.
So how do you determine where the isopleth is?
You have to know the system. And you have to know the total number of moles in the system, which we're not really given in this case. But we're going to assume one total mole for this problem, but it might be 50 moles. And so then you say, okay, of that 50 moles, how many total moles are in the top layer? How many total moles are in the bottom layer? And so these are the mole fractions. And so it'd be if I had 50 total moles and 25 of them were in this layer, then the amount of moles of nitrobenzene would be 0.83 times that 25, because that would be the total moles in that layer. And it'd be 0.17 times that total moles for the hexane amount. And so we will apply these different ratios to the total moles in each layer. But at first we have to figure out how many total moles are in the top layer, how many total moles are in the bottom layer. Okay. So let's do that for this situation. So reading the graph, the lever rule, that Z41 refers to the total mole fraction in our system, okay? And that it represents, again, the entire container. So Z is not for any one layer, Z is for the entire container, and it's split into two layers, and each of those layers has its own separate mole fraction. So A prime represents the values associated with a hexane-rich layer. Okay, and A double prime is the nitrobenzene-rich layer. So we've talked about this. I've just written it down so that you could review when you go back to this. And then these L values, these lengths, are the differences between the 35 and the 41, and the 41 and the 83. So these are the lengths of these two chords, I guess you would call them. And that's going to give us the ratio of moles. Okay. And so this is the lever rule written out. Now we can, later on in the review session, we'll do the lever rule on the PV phase diagram so that you realize it's not just for miscible liquids, it's also for any time you have two phases in equilibrium. So we'll do a PV example. I promise you that one. I'll work one out that we can do for that review session. And so then we have two equations and two unknowns. That's always nice. The one equation is the lever rule equation, and the other equation is the total number of moles in our system. So the total moles in this layer plus the total moles in that layer will equal the total moles we have. Okay, so we have those two conditions. A lot of times that one's not stated, and if you don't remember it, you can't do the problem. Right? So you get stuck with the ratio, but you don't know what to do with it because you forget that, oh, they also have to add up to the total moles. And if you don't know the total moles, you can at least assume one mole and add them all up that way. And so that's what we'll do in this problem. So we're going to assume that the whole system contains one total mole. So that means when I mixed in that 1 mole, 41% of that 1 mole was nitrobenzene, and 59% was hexane. That's from the isopleth. That's Z. Okay. So when I get to the end, if I add up all the nitrobenzene in this layer and all the nitrobenzene in that layer, it should add up to 0.41 because that's my total amount of nitrobenzene, and the hexane should add up to 0.59. Okay. Now using the lever rule, we just rearrange that and get this ratio of the total number of moles in A prime divided by the total number of moles of A double prime. And so then that equals length of A double prime over length of A prime. So 0.83 minus 0.41. Looking at the phase diagram, you should be able to figure out where these numbers came from. So you can calculate those lengths with the three numbers that we have, 0.83, 0.41, and 0.35. And so when you do those subtractions and then divide, you get 7. That's nice. Okay, so that just means that the number of moles of A prime is 7 times the number of moles in A double prime. So that's how I came up with this meniscus. It's not exactly to scale. This should be 1, and that should be 7.
Yeah.
Okay, but it'd be really tiny. Now that shows you also that when you have phase separation, sometimes it's hard to tell. You might have a layer that's so thin you just can't see it. And so you'd have a film on top or a film on bottom, and that's actually phase separation. But it's just so subtle because your curve is slammed all the way to the right, and you've got a tiny little amount of phase separation going on. So then we substitute that into this equation. So the Na prime is 7. So this piece goes in for this. And we have 1 total mole. This was an assumption. And so then this is going to be 1/8. So in the total number of moles in A double prime is 0.125 moles. So that's the total amount of moles in this bottom layer. And 83% of that total amount will be the nitrobenzene, and 17% of that total amount will be the hexane. And then we bring that back into our other equation, and so then we have 7/8 is the A prime. So 0.875 moles is the total number of moles in A prime. So let's apply these. We have the total number in A double prime, so let's now take 83% of that and 17% of that and see how many nitrobenzene moles we have in that layer and hexane, and let's do the same thing for the top layer. So to find the moles of each component in A prime, so A prime we have 0.35 moles of nitrobenzene in total moles, and so that we have the total moles of that layer. So we have 0.31 moles of nitrobenzene in this top layer. This is absolute moles, right? So that's how many moles of nitrobenzene in that layer. It's 35% nitrobenzene, but if you wanted to know the absolute number of moles of nitrobenzene in that layer, that's what it is. It's 0.31. And then the 0.65 would be the hexane, and so that would be 0.57 total moles in this upper layer in the hexane. And then to do the A double prime, it's 0.83. So it's a higher concentration of nitrobenzene, but it's a small amount of moles. And so we only have 0.1 moles of nitrobenzene in this lower layer. Even though it's the nitrobenzene rich layer, it's rich in proportion of nitrobenzene, but it's got a tiny number of moles in terms of our whole system, because the isopleth is so close to the other layer. And then 0.17 is the hexane percentage, and since it's a small layer, that's only 0.02 moles of hexane. So this tiny amount of hexane is existing down in this layer here. And so we've fully characterized the system. We know where our moles of nitrobenzene are in the two layers. We know where the hexane is. We know the composition of the whole. We know the composition of the parts. So we've fully characterized it. And that's great. Now, if this was the situation where you were trying to separate these two, just using phase separation or like extraction, you would say, well, I've taken this nitrobenzene-rich layer. It's 83% nitrobenzene. That's pretty good, but you've only got 0.1 moles of the total in there. Okay. And so you could fully characterize the system and know how efficient your extraction would be. And so this is what we would do for liquid-liquid extraction. We would characterize the system and see how efficient that is. Occasionally this shows up in people's research. Dr. Petrokovics was trying to extract one of her active molecules, and the molecule wasn't soluble in the organic phase, wasn't very soluble in the organic phase. And so one of her students came to me and asked me about solvent substitution. Can we change out that organic phase? And of course, it's a proprietary molecule, so they, said, promise not to tell anyone. I said, okay. So they gave me the structure of the molecule, and I typed it into my software and came up with the Hansen Solubility Parameters for that molecule, which solvents would be good for dissolving that molecule. And so we ranked them by best to worst, and like the third or fourth one down was cyclohexanone. And they're like, oh, we have that in the lab. And so then they went and used that different solvent. So I helped them choose a different organic phase, and more of that molecule went into that layer and improved their extraction by several times. So this is, again, you can change the composition of those layers to change the partition. And so we've got a partitioning here that's not really that great. It's only 83 to 35. The nitrobenzene is 83% in this layer, 35% in that layer. You'd really like it to be better. You'd like it to be 90 and 10. So you get a really big split, and that would be a more efficient extraction. So then you can check your answers in two ways, and this is nice. You can add up the total moles. So these are all the absolute mole values, so 0.31 and 0.57 and 0.1 and 0.02. That better equal 1 mole, because that's what we said was in the total system. And so that's always nice whenever you can check your work. Okay. And then you can also check up to see if it hits the isopleth value. So just looking at nitrobenzene, we add up the moles of nitrobenzene and we get 0.41 moles, and that's going to be our mole fraction in our isopleth, Z. So 0.41 divided by the 1 mole total gives us that Z value, which we started with. So that's always nice. We've pretty well exhausted the day, so let's pause and make sure that we understand the lever rule. It can be one of the trickiest ones because there's so many unitless values. All your mole fractions are unitless. Your isopleth, or not your isopleth, but your Z value is unitless. And there's a difference between Xn, so the mole fraction of nitrobenzene, and the absolute number of moles of nitrobenzene. So there's just a whole lot. Everything's a mole. And so you see how I did the problem. I put subscripts on everything. I put moles of nitrobenzene, moles total, moles of hexane, moles total. Your units are your friends. Use them. They'll keep you straight. Yeah. What needs clarification? It looks so easy when it's laid out like this. Yeah. No.
We'll see.
Yeah, we'll see. Okay, so try to find some lever rule problems. I'll look for you as well. See if you can do the PV one before we do it in class. So go back to the PV phase diagram and try to see how many total moles are in the gas phase and how many total moles are in the liquid phase when the molar volume is halfway in between. Okay. And so that one is a little different because we're not dealing with mole fractions. We're dealing with molar volumes and the amounts of substance that are in the gas phase and the amount of substance that's in the liquid phase. We should have done a Kahoot, but now we really don't have time. So we'll do a Kahoot to review the beginning of class next time. Don't let me forget. All right. Have a good day.